Welcome to the laboratory lecture video, blah, 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 whatever you want to call it, on lycopene in tomato paste. So in this lab video, we are going to talk about maybe why you're doing what you're doing or why you did what you did, depending on when you watch this. So I'm going to give you not necessarily a rundown of what we're doing in the lab, even though that's going to be part of this discussion, but why things are done the way that they are done in the lab. Because, you might have questions like, why did we add this and why did we add that and what was going on at this time if you've already done the lab. So this video is to really kind of gather all that information up, wrap it up into a nice little neat package, I hope, with a pretty bow, and then I can send it out to you and say, now it's yours. Open it whenever you can and watch it as fast as you can and answer those questions the best way that you can. So, lycopene and tomato paste, I'm not going to waste any more time, and the reason that we always start off traditionally with this particular lab experiment is because it gives you an introduction to chromatography. That's why we do this. So this is a brand new field. It's all about separation. And I think that this lab, at least I hope, hits home the idea that chromatography is separation at its heart. It's as simple as that. It is separating things from each other. And for this particular lycopene experiment, this is something that you can see a visual cue of what is going on. So, yeah, it's scribble, it's Scrabble, whatever. I just need a doctor's signature and I'll be great. All right, so visually, I can see separation. Visually, I'll be able to see colors. And it also kind of corresponds back to the whole idea of how chromatography got started. It was all about color rotting, and a lot of pigmentation was getting extracted and separated, and that's how this world of separation somewhat began. So I think it's nice and fitting that we start the semester off with that particular lab experiment. Something that we can visually see separate inside of a handmade column. And that's why we choose this one. Not only that, but tomato paste is pretty safe. So you can go to the grocery store any day of the week and buy as much tomato paste as you want. And you probably need 1 little teaspoon of tomato paste. And what do I do with the rest of the can? I mean, days and days go by. I don't need tomato paste again. And by that time, it's ruined. So what do I do with it? All right, well, that's up to you to figure out, not for me to figure out. That's not the purpose of chromatography. All right, so here is kind of a structure of lycopene. Oh my goodness gracious. Look at this, C40H56. There are 40 carbons in this structure and 56 hydrogens. Now, let's revisit a little bit of organic chemistry. Woohoo! I know you're excited with that. Whenever we talk about organic chemistry, we often talk about the world of alkanes. That is A-L-K-A-N-E, alkane. So alkanes are basically this concept that they are all single to single carbon bonds, right? So there's no double bonds, there's no triple bonds, nothing fancy, nothing crazy. It is just straight up single bonds all the way. Carbon is there. They're connected with one little stick. Even though they're not sticks, they are pairs of electrons. There's no such thing as a stick bond. And if you had me for organic, you would know that. All right, so anyway, what happens in the world of alkane is that, okay, well, here we get a carbon, and let's say there's 2 carbons that are connected together. All right, so here we have a hydrogen and a hydrogen and a hydrogen, and here a hydrogen and a hydrogen and a hydrogen. So if I take a look at this, it looks like if I counted everything up, this is 2 carbons, right? 1, 2. And then as far as the hydrogens go, this is 1, 2, 3, 4, 5, 6. All right, so there's kind of a ratio. I can deduce something there. There's kind of an ingredient recipe that I need to follow in order to make that carbon molecule, and that's going to be called ethane. Well, okay, if we do 3 carbons, 1, 2, 3, there is a hydrogen here and a hydrogen there and a hydrogen here and a hydrogen there and a hydrogen here and a hydrogen there and a hydrogen here and a hydrogen there. All right, so if I count the number, there is 3 carbons in total, 1, 2, 3. And then if I count the hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, all the way around. All right, so there we go. So the issue here that I'm trying to get around to is that for an alkane to exist, if that molecule is a carbon single bonded carbon, there's got to be a proper ratio between the carbons and the hydrogens. And if you've taken organic chemistry, if not, it's no big deal, but if you've taken organic chemistry, for alkanes, we will often see carbon with a certain number of them, and the hydrogens will be that certain number of them, and then it's actually going to be times, okay, look at this, 2, and then we get to 6. How on earth do we do that? 3, and then we get to 8. How on earth do we do that? Well, it's actually double the carbons plus 2 more. That is 2n plus 2. That is how this template works. So 2 times 2 is 4, plus 2, 6. And then if we look at the 3 carbon structure, that's 3 times 2 is 6, plus 2, 8. That's how this is going to work. All right, so let's look at lycopene, right? We got 40 carbons. So if this was a proper alkane, it would be C40, and then it's going to be H. Okay, 2 times 40 is 80, plus 2 is 82. Folks, that hydrogen's 56. There's no way this is an alkane. It's got to be something else. Well, the next kind of family that we can talk about is something called an alkene. And an alkene is a carbon that has a double bond with another carbon. At least one. It can have more than one, but at least one of those, then this structure is going to be called an alkene. Well, if I take a look at the name of lycopene, look how that ends. It ends in E-N-E. And over here is E-N-E. So this is probably named accordingly. It's letting me know, hey, all these carbons here, they're not single bonded. They could have double bonds in, if not more double bonds or other structures, but this definitely is not an alkane where it's just a simple little carbon, single carbon types of bonds. So lycopene is an organic. Lycopene, due to the number of carbons and hydrogens, it is fairly large. There's a lot of carbon here, a lot of hydrogen, so the solubility in water is going to be very low, and that's because lycopene is really truly an organic type of molecule. Lycopene is often found in some multivitamins. That's great. I mean, multivitamins can be an add-on. You're going to see there's a gender divide here. Is it men or is it women? Well, one group is going to go through and probably require a little bit more lycopene in their diet on a daily basis, and we'll talk about those groups a little bit later on. But because of this, there is regarded a nutritional content that we can get from lycopene. And because it's organic and because it has very low solubility in water, this is going to be a very fat-soluble, nutritional type of compound that our body can use in some form or fashion, right? That's what this is kind of leading up to. Lycopene, as you can see in the picture, does have a color, and this color is often going to be red, or it's going to be a darky orange color. So we can visually see that. And if you've taken the spectroscopy class, what we have discussed in spectroscopy is if something is colored, it really has a chromophore on it. That's the proper definition of that. And that chromophore is going to give us a certain hue, a certain color that our eyeballs can pick up on. Now, not necessarily, right? I mean, but a lot of times colored things can be ran in UV vises, and colored things have chromophores on them. And lycopene is a colored thing, so there's probably a chromophore on this as well. One of those chromophores, again, if you've taken 240, if not, no big deal, is called a conjugated double bond. So what a conjugated double bond is, it's a carbon that maybe has a double bond to another one, and then we skip one. We skip a beat, and that's a single. And then it goes back to a double, and then it goes back to a single. So that is what we call conjugation. So a double, single, double cause you trouble type of situation. That's kind of how I like to think about them, because the reason I say they cause trouble is through reactions. They give us unexpected products sometimes because those electrons move throughout the molecule. So fat soluble, great. Conjugated double bonds, that's what gives it a chromophore. That's why we see color with our own eyeballs. And if you take a look at the other enes that might be present, you will often see related structures that are very similar, aka carotene, that is in a sense an organic, absolutely, but a sister molecule to lycopene. So there's a slight differences. Carotene still has 40 carbons, but the number of hydrogens are going to be somewhat different. So because of that, we need to talk about some of these things as well. There's a very common structure. It is going to come along with something like a tomato-based product that is going to be present, and that maybe is going to look a little different, but you know, it's along for the ride. I mean, when you see one, you probably are going to see the other one here. All right. Pigment is often red, but as the note says on the slide, you know, asparagus and parsley also contain lycopene. Not a lot of it, but it's there. It can be extracted. It can be found in small quantities. But absolutely, if you're wanting a large amount of lycopene extraction from a product, you're probably going to look at red things like tomatoes because they probably are going to carry it. Carotene, it's going to be an orangey color, so think of carrots, right? How often have you said, well, Bugs Bunny eats carrots all the time. He's got eyeballs, you know, with 20/20 vision. All right, so a little bit of organic review that just took place, but there's going to be some other terms that we want to talk about as well, and that is the difference between a saturated and an unsaturated type of compound. So saturated compounds mean that all of the carbons are single bonded all the way through, no exceptions. Unsaturated is at some point in time, you're going to have a maybe bond that's a double bond or a triple bond. They're not all single bonds all the way through. So this would be an example of a saturated molecule, and this would be an example of an unsaturated molecule. So when we begin to look at the structure of lycopene, really chemical formula wise, absolutely, we're going to look at that in just a second. We're going to be able to determine, is this a saturated or is this an unsaturated compound? You could probably already answer this question, because if all the carbons had single bonds all the way through, I already told you what that's called. That's called an alkene. An alkane. And those alkanes have a template. They have a structure that's they like to bring to the table. And that is a certain number of carbons, and hydrogen is 2n plus 2. And we already said that lycopene does not match that category. So that probably means lycopene is not saturated. So we probably are going to expect some double bonds into the picture. And ENE endings are going to give me an idea of that. The other terms that I want to talk about is cis and trans, and these are often called E and Z, even though they are different. So we need to dive a little bit deep into the discussion here of what this is all about, and this is the driving force for the lab here. So here's going to be my lecture on cis and trans. Whenever we deal with double bonds in organic chemistry, we see the carbon double bonded to a carbon, and there's always like kind of an up and a down type of situation that it forms. The structure or the 3D geometry here turns into something like a trigonal type of shape. So you can kind of see that the carbon is kind of on one side of the triangle, and then when it goes up or when it goes down, we could probably in a way connect those two lines that I've just drawn to make this full triangle type of shape. Well, all double bonds, when they form, will give us this type of geometry. And it's going to be very important sometimes to figure out the orientation or the shape of these types of molecules when they begin to show us these types of things. So what's going to happen is that, let's say I get a compound up here and there's something attached, and this is just a little simple O hydrogen. And then let's say that I have another thing that's going to be attached. Who cares what that is? It's just a random R group. And let's say there's a hydrogen in that spot. The criteria here is that, they've got to be two different things on each of the carbons, meaning the carbon on the left, it can't be both hydrogens, okay? We've got to have some type of random group on one side and hydrogen on the other. On the right-hand side carbon, again, those two things need to be different. So they cannot both be hydrogen. One can be hydrogen, but the other one has to be something totally different. Those different things do not have to be the same on both of the carbons, meaning that this group up here that I'm going to call A and this group down here that I'm going to call B, they do not have to be exactly the same. It does not matter. They can be different. It's no big deal. Cis and trans is still going to apply in this type of situation. So that is one way that things can attach in 3D geometry as far as organic structure goes. All right, well, another option for a double bond is carbon-carbon like this, and I still get these kind of spokes that come out in triangle wheels. And let's say that this group is up here still, and I'm going to still call that one A, and here's my hydrogen. But let's say now on the right-hand side, my random group, whatever that group might be, is up here at the top, and that is a B. And then down here is going to be another hydrogen. So this is another option, right? And sometimes I don't have control of what forms. It's just going to form. And sometimes there is a preference of one version over the other one, but that is a molecule decision. That is not a me, Tracy decision. That's not a you, whoever you are decision. That is a molecule determination of what is best for its particular compound. But there's two different options here that we can look at if we just focus around that double bond on how these molecules can connect. So cis and trans actually relates to something very specific, and it relates to the hydrogens that are on the double bonded carbons. It does not relate to the groups that are on the double bonded carbons. So cis and trans is a hydrogen driven decision. So if you do not have a hydrogen on one side and a hydrogen on the other side, you cannot use cis and you cannot use trans. Hydrogen has to show up, one has to show up on each of the carbons involved in the double bond. So if the hydrogens are on the same side, then this is what we call the cis form of a molecule. So that is the cis formation around that double bond. If the hydrogens are opposite of each other, then this is what's going to be called the trans orientation of that particular molecule. So the structure on the left is the trans version of the double bond, and the structure on the right is the cis version of the double bond. So that's a little bit about cis and trans nomenclature. So what about E and Z? How are these different? Are they the same? Why do we talk about two of them at the same time? Well, here's the kicker. Let's say that, I didn't do hydrogen, and maybe I'm not going to do hydrogen here either, or maybe even there. I mean, hydrogen can be there, absolutely. But what if one of those sides did not have at least one hydrogen attached to that carbon, but something else? All right, so here we're going to do something a little bit bigger, not just a little bitty blue dot, but we're going to be a big old blob, and I'm going to call that B. And we'll keep the hydrogen there in that situation. And then over here, I'm going to do another big old blob, and we can do it there. And then another big old blob down here, and we can do that there. All right. So as far as E and Z concerned, it is the same mentality. But we're going to run into instances where these carbons that are involved in double bonds, they don't maybe have at least one hydrogen on each of those carbons. And that's okay too. We just don't use cis and trans for that nomenclature. We switch to what we call E and Z. And what we're looking for here is a ranking. That ranking's not going to be important. We're not involved in an organic chemistry class. But we need to rank these types of things and give them priority. And very often, size can be an indicator. It's not the true type of definition, but it can be an indicator of what we need to prioritize. It actually goes by something a little bit different. But in my drawing and in this example, I'll give you kind of just, oh, we'll do size and just pretend like that's not true, because it might not be. All right, so over here to the left-hand side, this is a molecule, and it looks like this is priority because that's a little bit bigger, right? And then over here, we get hydrogen, and then here we get a dot. Well, okay, let me just switch those positions around. All right, I'm doing it for a reason. Bear with me. And then here. So this is just a simple little O hydrogen. It's the smallest atom on the periodic chart. And then up here, whatever this is, then that's going to be the highest priority because it's going to be bigger. So hydrogen, again, tiniest, smallest, everything's going to beat it out. So the higher priority one is going to be the dot that I drew above that hydrogen on the right-hand side. And then on the left-hand side, let's say there's two atoms that are connected to that carbon. And we're going to look at the biggest atom in a way. And that's going to be down below that I've labeled as B. So if I take a look at that orientation, they are still opposite of each other, okay? And that means that that structure is an E form. So that is what we use instead of trans. So trans would be the idea that hydrogens are opposite of each other. And the E form means that atoms other than hydrogen are opposite of each other. Okay, that's why we use that term. Over on the right-hand side, we'll do the same thing. If I take a look at the left-handed carbon, this one is a bigger atom, so I'm going to give preference to that one. Here, that one is a bigger atom. I'm going to give preference to that one. And if I do that, it looks like these groups are on the same side. And that is the Z form. And I often joke and I say, I feel like I'm a German. Z groups are on the same side. So as long as you kind of keep that in mind, then that is what the Z is going to represent. So what this means is that if you have a cis structure, that's great. But again, these are in reference to hydrogens being on the same side of the molecule. And then if you have the Z form, that's also great. That just means atoms are on the same side of the structure, and those atoms are something other than the hydrogens that we're trying to compare and contrast. So if I take a look at the lycopene, woo, doggy, look at this. There's my structure. And if I look, oh, look, unsaturated, 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 unsaturated everywhere. So double bonds are loaded in this molecule. And then if I take a look even closer, look at what's happening. Double, single, double, cause you trouble. Double, single, 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 blah, 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 blah. Well, that means that this is heavily conjugated. And if it's heavily conjugated, guess what? Color! And I see red and I see orange and I get to run them on UV. And that's why we kind of do what we do at the end of this experiment. And that's why we do the analysis piece. And we can do that because of the chromophore that is with lycopene. This is lycopene, folks. And if you take a look, it's all carbon, it's all hydrogen, it's very long, it's very bulky. This thing is big. And overall, there's no polarity. This is very organic-y in nature. There's no oxygens that carry free pairs. There's no chlorines that carry free pairs. There's no nitrogens that carry a free pair. I mean, for the most part, this is pretty much bland, vanilla, ice cream, organic type of molecule, what this is. So that is the structure of lycopene, and that is what we're trying to extract out of the tomato paste. So, with that said, water probably should not be used to extract lycopene from the tomato paste because it's not going to work. Water is a very polar molecule. And folks, hello! this is very non-polar. I don't see polarity in the molecule at all. So therefore, polar and non-polar do not mix. So that is why we do not use water. If you look at the lab directions, it's going to tell you, oh, use something like hexanes. Well, hexanes is very organic. Hexanes has 6 carbons in total. It's different orientations of how the 6 carbons can come together, but it is 6 carbons. It is organic. It is nonpolar, and like dissolves like. So that is why we focus on hexanes in this particular step, because hexanes is going to go in, it's going to be able to grab the lycopene, which is very heavily organic, and it's going to be able to pull it out and extract it, and that way we can put that extraction into our handmade column, and we can visualize and see this separation take place. Couple of health benefits for lycopene. I mean, why do I want to care about it? Why do I want to take it? Why are they putting it in multivitamins? Well, okay, here are some of the reasons. Well, for men, well, it's prostate cancer. Now, I need to say it does not prevent prostate cancer. Hello, right there, big letters, does not prevent. But it can help the healing process after any type of prostate surgery, prostate cancer surgery, or whatever the case is. Often, if this is a problem, maybe genetically for your family or for you, then don't be surprised if they give you a lycopene supplement or something that contains lycopene a handful of weeks before the surgery date is supposed to show up. So that way it can be into your system, it can be there, it can help you out, and after the fact, after you get out of surgery or some type of operation, then the lycopene can somewhat kick in and help you heal a little bit faster. So that's great news. So if you, have that kind of gender or sex for men, then something not to snarl your nose about, right? I mean, take some lycopene. I think that'll help you out. It's not going to hurt you by all means. And then for some people, I'm going to get it naturally. I'm not going to take a supplement. Okay, then eat tomatoes. All right. So that's the thing. Eat your fruits and eat your veggies. Those are nothing to snub your nose at. So eat them. Make sure you get that intake. For women, so for women, breast cancer, it does help prevent that. And that is one of the reasons that if you do take a multivitamin, for women, they will include lycopene as an additive. You don't really see it too much on the men's multi-tablets, but you will see them very often on the women's side of the house. So lycopene will be an add-on to that multivitamin. It does help prevent breast cancer, so take it and take it religiously and help you out, right? Again, it's not going to hurt anything if you do have it, but it could also help prevent some things or prevent some things from getting worse if you're prone to it. What they've shown is that in mice, if they inject them or give them some lycopene supplement, it significantly actually decreases the breast tumors as well. So it can help prevent those tumors from taking place, help slow them down, and maybe even shrink them a little bit. So again, nothing to snub your nose with. So if you are a woman genetic-wise, then absolutely make sure that you take your lycopene supplement. Research also shows that lycopene does a great job to help prevent lung cancer as well. So, yet again, another reason to take it, whether you're a man or whether you're a woman. It does not matter. Lycopene will help you out in each one of those cases. So, keep that in mind the next time if you do take a multivitamin, look out for those lycopenes, look out for those supplements, because, again, they're not going to hurt you. Tons of journals, tons of articles that are out there about the effects of lycopene, and commonly found, of course, in tomatoes and tomato paste. It's just a concentrated version of it. So you can find these all over the place. You can go into Google, search for them, find them like little candy. I mean, come on now, they're everywhere. So if you get the time, do it. Test that process, and you'll see all of the health benefits that are associated to the lycopene structure. The lab scenario that we're going to kind of do here in this particular activity, it says, consumer advocate is investing the quality of food. They believe that processing foods will degrade the color and the flavor and the nutritional value of the product. Lycopene exists as the all-trans isomer. Now, all-trans is kind of funny because, you know, greater than 90% of the lycopene structure that's naturally in that type of product will be in the trans form. Now you know, why did I talk about cis and trans and E and Z for 14 hours? Well, it's because trans is going to be related to the lab, and we're going to have to figure out what this actually means. So that means that lycopene is going to be in the trans form, and that trans form basically means here's a carbon double bonded carbon, and a high priority group will go maybe pointed down, and the other group will be pointed up. These are high priority groups that will happen here. That is the structure of lycopene that we need, and that's the good lycopene, and that's how lycopene should stay. But the problem here is that heat and light and certain chemicals can actually make that flip. And when we make that flip, we get the cis form of the structure. And the cis form would be, of course, the carbon double bonded to the carbon, and the high priority here and a high priority there. So this is the bad form of lycopene, and your body actually can't utilize that for anything. So what's funny is that when they make tomato paste, I want you to think about how they do this. They're going to take tons of tomatoes probably, and they are going to heat them up in order to make something like a tomatoey type of soup. So hello, heat! And then in addition to that, they are probably going to thicken this soup up, and then they are getting closer to something that is like tomato paste. It's probably exposed to light as they do this. They're probably not keeping covers on things, because if they kept covers on things, what's going to happen? Well, nothing will evaporate off. Nothing will get thicker. You need to evaporate some of that moisture off of there. So light energy, hello, and we shorthand that as with HV. If you've taken spectroscopy, you know what that means as well. And then we're not only hitting it and slapping it with heat, we're not only directing light down as this kind of manufacturing process takes place, but we're also putting it in cans or putting it in containers, and we are probably somewhat pressurizing those cans after we get finished with those. And that probably means taking it to high heat again in order to save and preserve them so they don't mold or spoil over a course of time as it sits on the grocery store shelf. So how much of this is actually going on? Because now I know, oh my God, I've got trans version that's good, and they're using all the heat, and they're using all the light, and they're using these high pressure, and they're generating a product, and that product could actually convert that to cis. And even though it's still lycopene by definition, it is not the good version of lycopene that actually helps me prevent some of the cancers that we just talked about. So the quality of the lycopene is very important. So very, very high levels of the cis typically means it has been overprocessed or excessive heat has been used in order to make that product with. So as I look at the brands of tomato paste on the grocery store shelves, I'm now inquiring, how did they manufacture that product? Because one quality of tomato paste scientifically actually might be more beneficial than another manufacturer's version of tomato paste. That's what this is all running into. That's what we're talking about in this lecture video, or this lecture/lab video. So that's one of the things that we're going to be doing. We're going to bring in different brands of tomato paste, and we're going to analyze them, and we're going to look for the concentrations of trans and cis lycopene from these different manufacturers. And folks, listen, you know, if they are adding the lycopene as a supplement, that supplement has to come from somewhere, and that could already be a powder, and that's great. But how much of it is trans and how much of it is cis? How pure is that lycopene that they are using, that they are putting in these supplement products for you to take? Because yes, it can be lycopene, but if it's the cis version, or if it's a high percentage of the cis version, it's not as good for you as a good quality lycopene product. What happens with the structures with lycopene when the cis begins to form? Hello, folks, here we go. So up here at the very top, this is all trans lycopene. Look how straight. Oh, look how pretty. Look how symmetrical. We love those types of things, right? Especially in organic. So that is trans all the way. The structures or the groups that are important are opposite of each other. So if I focus on one of these double bonds, it doesn't quite matter. There's a double bond. Notice that this somewhat points down and that somewhat points up. So they are pointed in opposite directions, hence a trans version of the molecule. There's no cis here at all. That is 100% trans. Great quality lycopene there. That's how it should be. However, each one of these double bonds can create a point of a twist. So when lycopene gets hit with heat, when lycopene gets hit with maybe light energy, whatever the case might be, a chemical reaction takes place. We can get a flip at almost every single one of these double bonds, right? We can. So all of these are versions of a cis molecule where the molecule kind of goes straight, and then it turns a curve. And then and it turns a curve, and it turns a curve. So it begins to twist, it begins to change its shape, and shapes are very important things when it comes to biologics. So we often play on the shapes of proteins. We often play off of the lock and key models, and lycopene is no exception. So our body really likes the straight and narrow trans lycopene, but the more cis that we have, the lower grade or the lower quality lycopene that we have on our hands. So in the next video, we'll pick up from here and we'll continue to talk about lycopene and the lab experiment and why we do things the way that we do. And we'll talk a little bit about the final calculations that you should be performing at the end of this experiment.